draft physics video. Comment. I guess I'll do some reading first. This one, I guess we'll just do the subject of how fast something has to move to create sound, or what sound is, basically that kind of thing. And yeah, there's one comment that'll probably be enough for a video. Anyway, parapolylogic. I don't know what that means, but it sounds kind of spooky. Anyway, one example of an object making a sound at less than the speed of sound is an airplane traveling at 250 miles an hour. No. I mean, you know, it can be, except for air turbulence, there isn't any sound without the engines running. You can't count engine sounds. They're moving faster than the speed of sound, you see. So, gliders, for example, pretty quiet. Just depends on, like I said, how efficient the airfoil is in terms of you can create sound through creating turbulence, which is molecules moving faster than the speed of sound. Anyway, the speed of sound is 767 miles per hour. The speed of air molecules at room temperature is 1,038 miles per hour. Well, I just think those numbers are kind of meaningless, so I guess we'll go to the videotape. I'll do a drawing. As I've argued, all wave happenings that are real waves in mediums, not stuff like bullets moving in a wave. It's not a medium, really. It's not a phenomenon of the medium. There's not a medium of bullets and then the bullets wave through the medium of bullets, that kind of thing. So, you know, the same word is used for these very different phenomenon. One thing where you have actually something new introduced into something and it's traveling through even empty space, and it can appear like a radio wave going through empty space. It's not in any traditional sense of wave, in the sense that it's not a pressure moving through a medium. Well, it isn't in my opinion, because I'm not counting the electric and magnetic endless perpetual fields that are somehow created in some sort of notion of the Big Bang, I suppose, right? So there's somehow a limited amount of that field or something. I don't know. There's nothing. The conventional description lacks description of anything. Alright, so anyway, but there's always tension is the point. So when mediums convey waves, it's because they're under a tension of some kind, and you violate the tension in the sense that you go faster than the tension can deal with what you've done, and therefore you create a wave of pressure that goes through the rope or whatever you've put under tension. So the tension in air is the molecules, and there's two things working against them. There's gravity is pushing them towards each other, okay? So that pressure, that's the air pressure from gravity, and then you have heat, which is pushing them away from each other, because they're all absorbing and re-radiating heat, which is really just, you know, a form of light, but it doesn't really matter. It's quanta. So it's the same as electron force or proton force. It's a magnetic energy essentially. But anyway, the heat is pushing them apart, and so that's the tension. The tension is between gravity and the heat, which keeps these molecules moving, you know, relative to each other. Moving in going somewhere to velocity is kind of nonsense. So they're all just shuddering in these positions, and they can slide across each other and do that kind of stuff, but there's no real movement. Now, the argument I'm making is that it takes what the speed of sound is based on is the amount of time it takes for something to react. So when these two objects end up moving closer to each other, there's an amount of time it takes for this molecule to, say, move away in some direction, some place where there's less pressure. So if one molecule, its heat radiation, gets to this other one that has more heat radiation hitting it, this out. I can try to draw that, but I don't know if there's any point really. So it's got this heat is pushing on it. It can move at a certain speed away, and the speed of sound is sort of based on how fast it can do that. So when you have an incursion, you know, that's slow, that is, the thing moves slowly, you know, into some other thing, then the other thing can move out of the way in any direction. There's no urgency. You know, the balance will take place. So that's the thing to understand, is because of this gravity thing and this heat thing, what tends to happen is all of the molecules end up trying to space. There's a tendency for the spacing to be even between everything. Everything tries to balance the pressure. It doesn't try to, don't get me wrong. That's just the effect. The effect of the applied general pressure is that all the constituents will sort of nudge each other until they're all equally under pressure. And if one thing's under more pressure, it'll push harder, in a sense. So the closer you get, the more pressure you get. And so what's happening with sound, when it gets, you know, I use the analogy of pool balls. Maybe I'll just go back to that. So if you have pool balls spaced at a certain distance from each other because of that equalized pressure, and you move one towards the other, the pool ball can move this way or this way. It can do lots of things depending on the pressure. So if there's more pressure coming this way, it can go this way. If this guy's further away, say this one's a little bit further away, it can go that way to relieve the pressure. But what happens when you move something fast enough is that you violate the speed at which the thing can mitigate the pressure, and it just passes it on. So this extra bit of pressure just gets passed on to the next guy, and then that guy passes it on to the next guy, and this guy passes it on. So it's sort of the pass-on speed. So if you hit it hard enough, so if I push that string of pool balls slowly with my finger, just move it slowly, you can sort of understand that nothing dramatic is going to happen. Things are just going to go off in different directions, and there's not going to be any action. But if I hit this one hard enough, then it's going to violate this one's space, and it's going to create a very high pressure, and that very high pressure is just going to force it to pass it on. It's just going to move straight and into the next guy, and then into the next guy, into the next guy. And so I don't know exactly how to point that out, that there's a difference between having time to, it's like the tennis ball has a certain compression time. You know, it takes a certain amount of time to compress it and then for it to release that compression. So the release of the compression would be like you could have that as a constant or a standard, and that's the compression rate of a, you know, and it's based on the how much air is in the tennis ball, and you know, how highly it's pressurized. And so that's sort of the definition of the speed of sound, is what's that time it takes for that relaxation to take place. And if you force it to move faster than it can do that relaxation, you know, that relieving the pressure, then you have the potential to create this wave phenomenon. Yeah, I think that's adequate. Alright. Back to the reading and such, I think. Alright. So at room temperature it's 1,038 miles per hour. According to what you're saying, if an airplane moving at 250 miles per hour produces sound, which I think we can agree is the case. No, I don't agree. And I agree that, and I contend that if it does make a sound, the sound is coming from something. Okay, something where there's turbulence, like air is still going through the engines, and it's you know, going across the blades, or it's doing something, and that's what sound. Whatever sounds you hear are sounds of the whistles created in certain locations where something's flapping or vibrating. then the speed of sound must be less than 250 miles, and the speed of air molecules must be less than 250 miles per hour. So yeah, no, I don't accept your premises, and so yeah, I don't no, I don't agree. Sound waves can pile up on each other. So again, I'm saying that they really can't pile up. You know, I mean, all you can do is it's, you know, the Doppler effect, I guess is what he's going to get to. But that's not piling up. That's just shortening the frequency between the waves. It's not making a bigger wave. So you got to be real careful about the word pile up. You know, you can just change the frequency. Adding to each other's amplitude. See, they don't add to each other's amplitude. I mean, amplitude is how loud the sound is, not the frequency of the sound. So it's not adding to the strength of the wave. It's just changing the frequency. That is, how much distance, how great that pressure is in a sense. The tightness of the pressure. As well as cancel each other out. Well, canceling each other out is another word game, but that would just be that you have a low pressure mixing with a high pressure, and you end up with a neutral pressure again. So yes, if you mix high pressure and then pour low pressure in, you'll get no pressure. So you know, it's just addition. Okay, anyway, the Doppler effect is a familiar experience which demonstrates this principle. Well, again, now all it demonstrates is that the individual waves, instead of being an inch apart, or a half inch apart, or a quarter of an inch apart, they're further apart in the sense of the pressure, the section under pressure. So let me draw that. So you could have this whole field. Let's see, I guess if I make equally spaced objects, I might be able to explain this. Might be able to. Alright, so they're all they tend to want to be evenly spaced, and so you create this extra tight pressure at this location. Well, what's going to happen is this location is going to re-expand to its normal when it gets rid of the pressure. And this one's going to tighten. So this will be the tight one. And then the ones above it are the same as they were, so their spacing is still the same. So the pressure, the tightness, is what's going to move as the wave, is the pressure. So it's always a pressure that's moving, not the objects, in the sense that this object doesn't shoot this way to the head of the line. It just transfers pressure to the next guy, and so all you're doing is transferring the compression. So it's just a compression that just gets transferred. And again, it's the relaxation speed, the speed it takes to undo a pressure, is the barrier speed. That's the speed that'll decide what the rate of transfer of the pressure is. I think I said that okay. Whoa. Whoa. It's always really exciting. Kind of a negative way. Yeah, I'm sure it wasn't much of an experience for you either. It's getting this distance thing right. I gotta just push this monitor back, I guess. That would be the clever thing to do. Alright. It would be the clever thing to do, but I haven't mastered it quite yet. Alright, there. I think I've mastered it now. Alright. Alright, so where were we? Doppler effect, familiar, okay. Causes sound waves emitted from an oncoming object to have higher pitch, and sound waves emitted from an outgoing object to have lower pitch, like a passing train. Well, again, these aren't, to call that piling up, I think, is inaccurate. It's just changing the distance or the time, but it's not piling up. Semantics. There's a difference between the wave getting bigger and this distance between the waves changing. Alright, when an object moves at supersonic speed, it causes an extreme case of the Doppler effect in which the sound waves can't get out of each other's way and are forced to constructively interfere with each other. So again, I just totally disagree. And that exactly what happens when a plane goes supersonic is just happening on a much smaller plane scale. So if you think of an atom as a jet, when you force the atom into another atom at this supersonic speed, you do the same thing. You create a sonic boom. And it's just a real little one because they're just little atoms. But that's that's the source of it. So there's no yeah, I'm just saying it's always created by something moving faster than the speed that the atoms can relax at, that they can mitigate pressure at, they can relieve pressure at. So when you go a certain speed into them, they can't displace the pressure, just like the pool balls hitting them slowly, they can mitigate the pressure into the field. But when you hit them fast, they can't mitigate the pressure into the field. They can only pass the pressure on. Okay. Extreme case of Doppler in which sound waves can get out of each other's way and are forced to constructively interfere with each other. No, they do get out of each other's way in the sense that there's always a frequency. So I just fundamentally disagree. And as stated, once you go faster than the speed of sound, all you're doing is putting the sound ahead of the other waves, so there's no pressure. There's no extra pressure because that part of the field hasn't been disturbed yet. If you go faster than waves can travel, like on an ocean surface, and you move faster than the waves are going, you can make new waves ahead of the waves that are coming, and they're not going to have much to do with each other. Alright, what is the evidence that air molecules' distance from each other is dictated by the pressure of their electric or magnetic force? Well, it's dictated by the expression of that, which is the absorption and readmission of heat. And technically that's done by the electrons, I think. And so that's essentially turned into their repulsive effect with each other, how much their I've sort of diagrammed that, but I mean, as much as they say electrons have a certain charge, that charge changes depending on what force is going through the electron. So how much of two electrons repel each other is dependent on what's trapped between them. So yes, when there's more heat, there's more stuff bouncing back and forth between the electrons. So that's what I mean by that's the force that's keeping the atoms from combining, is the fact that the electrons are hostile to each other. And when they're hot, they're more hostile, essentially. Alright, what is the evidence that air molecules, their distance from each other is dictated by the volume number of molecules? No. Well, I mean, obviously, to some extent, it's a balance between if the atmosphere was in a closed vessel, a glass jar, well, that would be true. But they're in an atmosphere that can expand if it had to. So it can always fight against gravity. So if you make the heat high enough, gravity will lose a little bit of its advantage, and the volume will expand. But yes, if the volume can't expand, then yes, it's just more pressure, but you can't change the distance. But that doesn't have anything to do with how well the molecules can displace pressure, how fast they can dilute pressure. It's like you're going faster than the dilution speed. Alright, what is their distance from each other is dictated by volume number of molecules. So again, that's not really, no, it's dictated by how hot they are or how much gravity they're in. And those two components will dictate how far apart they are, the molecules. Electricity and magnetism have nothing to do with sound propagation. Well, I'm arguing as a physical reality view, electrons and force have everything to do with every single thing that happens. Nothing happens that doesn't involve electrons and photons in one form or another. A ton in one form or another. Nothing happens. And when you move your hand through the air like that, it does make a sound. No, it doesn't. So when I do this, there's no sound being created. It doesn't propagate the pressure. This pressure just diminishes. It just falls apart right around my hand. And that's it. It doesn't have any, it doesn't propagate through tension. So again, you're sort of not getting my point that there's a difference between things bouncing off of each other, you know, in some way, and then things compressing into each other and then rebounding from the compression. And like I said, it's kind of a violation of space. You could think of it as a membrane, and everything bounces around in the heat, and you can call that the membrane. They don't really create high pressure because there's no high pressure in the environment to create a violation of the membrane. But once you force the tennis ball to dimple, then you create the rebound effect. So it's like the tennis balls can be bouncing around in an energetic, like you have little styrofoam beads that are flying through the, in a thing or something, and the tennis balls get hit by little beads and they move into each other and move around each other. But it's not until you create a source of pressure that actually compresses one of the tennis balls that you end up with the rebound pressure. And that's what a wave is propagated by, is the rebound to the pressure violation. Alright, and when you move your hand through the air like that, it does make a sound. No, it doesn't. And it could be measured by a significantly sensitive microphone. I completely disagree. I don't think there's any evidence that anybody's ever detected moving something slowly from a distance. So I could take a real heavy object and move it slowly, out in the driveway or something, and you won't hear it. Once you get far enough away from the wind created by it, there's nothing. There won't be any frequency. There won't be any. It won't have any going power at all. And I could take a tiny object and spin it fast and make a sound that'll go 100 miles. So I mean, it's obvious, in my opinion, that those are fundamentally different things that are happening. The sound is an efficient transfer of pressure, where movement creates a slowly dissipated transfer of pressure. One's the rebound, and one's just rubbing, bouncing around. I don't know how to say that better. It's probably a better way to say it, because they don't really bounce. Bouncing would be a rebound. So they just roll across each other without creating any high pressure. You need the high pressure. And the way to create the high pressure is to move something fast. So again, I'll go back to the pool balls. I think it's a good analogy, because anybody who's kind of dealt with those kind of hard objects can, I think, understand. If I move the cue really slow into a string of balls, that the balls aren't going to go forward in any kind of way. There's not going to be any coherent transfer of that energy. It's going to be just spread and dissipated. And if I just take a little poke really fast, that'll shoot right through all of them. Alright, so I think that's probably enough. I don't want to keep revisiting this subject. I mean, if you want to make some counter arguments, okay, but I'm probably not going to, I don't have any interest really in, I don't think anyway, I don't think this is critical to the physics theory in any way. But maybe, I mean, it's just still understanding that everything's a nuclear force. I mean, everything's happening on the little bit scale, and the little bit rules are different than these big bit rules. And fundamentally, yeah, and there's also this argument that there's tension is essential to all wave transfers. There can't be waves in a medium that isn't under tension. I mean, that's a rule, and the rule should apply to sound, because sound is traveling through a medium of elemental substance. It is like waves in water. I mean, it is yeah, I mean, it's like other kinds of waves, sound waves, in that sense that it's a transfer of pressure through a medium. And again, that's different than waves created by introducing a bunch of particles at a frequency. Those two things, a wave of bullets is different than a wave of water. And what else has to be stated? So it's all nuclear. It's well, I'm just saying that, yeah. I'm just saying that I don't think you can come up with something where a sound is produced, that is something that propagates through the medium efficiently, that isn't related to something moving very fast. Okay. It's all sonic booms. It's all stuff moving faster than the medium can deal with. Okay. I kept saying that over and over, but anyway. That's the rule. Sorry. I mean, I suppose you could do this with water. You know, the analogy probably is suitable. You know, you put your finger in the water slow enough, you know, it won't propagate any waves. But you put a tiny, like just a pinhead into the water fast, and you get a whole bunch of waves. So anyway, oakley doke. Till next time and such.